Okay, good morning one and all. In the last sessions, we have discussed the different types of feedback configurations. That is voltage series and voltage and feedback configurations. So in that we have discussed the voltage gain, input impedance, output impedance, bandwidth and offset voltage with feedback. Okay. See here. So now we will see about what is voltage follower. What is voltage follower, right? So see this circuit diagram. So here the input is applied to the non-inverting terminal. So the plus is a non-inverting terminal and minus is a inverting terminal. So input is applied to this non-inverting terminal and the output is connected to inverting terminal directly the output is connected to inverting terminal. Okay. The lowest gain that can be obtained from a non-inverting amplifier with feedback is 1. So the non-inverting amplifier lowest gain is 1. The non-inverting amplifier lowest gain is 1. Okay. So when the non-inverting amplifier gives unity gain, it is called a voltage follower. When the non-inverting amplifier gives a unity gain, that is called a voltage follower. Voltage follower, as the name implies, the output voltage follows the input voltage. Okay. See here, the output voltage follows the input voltage. So that is called a voltage follower. So in this voltage follower circuit, input is applied to the non-inverting terminal and the output is directly connected to the inverting terminal. Okay. So this circuit is a non-inverting amplifier circuit. This circuit is a non-inverting amplifier circuit. So why? Because here the input is applied to the non-inverting terminal. So in the non-inverting terminal, in the non-inverting amplifier, the voltage gain is less than 1. If the voltage gain is less than 1, that circuit is called as voltage follower. Okay. Here V out equal to output voltage equal to A into VD. So VD is the difference voltage. So VD is the difference voltage, that is equal to V1 minus V2. So we know that A equal to V0 by VD, right? So from this we can write V0 equal to A into VD. Here V1 equal to V in, and V2 equal to V out, right? So here V1 equal to V in and V2 equal to, so this voltage is V1 and this one is V2. Here V1 is V in and V2 is V0, that is V out. Okay. So here V1 equal to V2 if A is greater than 1. V1 equal to V2 if A is greater than 1, right? So from this we can write V0 equal to V in. V0 equal to V in. So the output voltage equals the input voltage. So in the voltage follower circuit, the output voltage is equal to the input voltage. Okay. So it follows the input voltage. So that is the voltage follower circuit. Here input voltage is applied to non-inverting terminal and the output is directly connected to inverting terminal, right? So here the voltage gain is less than or equal to 1. So that is the voltage follower circuit. Next, see the differential amplifier. So see the circuit of differential amplifier. Here we are having two inputs, VA and VB. So VA is applied to inverting terminal and VB is applied to non-inverting terminal. Okay. So here we are having feedback resistor RF. So the output is connected to, again the part of output is connected to input side. Since there are two inputs, so superposition theorem can be used to find out the output voltage. Since there are two inputs, here we are having two inputs, right? So that's why we are using the superposition theorem to find out the output voltage. So when VB equal to 0, the circuit becomes an inverting amplifier. When VB equal to 0, the circuit becomes a inverting amplifier. So the output due to VA, the output due to VA is, so that is output due to VA, that is equal to minus RF by R1 into VA, minus RF by R1 into VA. Okay. So if VB equal to 0, the circuit becomes a inverting amplifier, right? So for the inverting amplifier, the output voltage is minus RF by R1 into VA. So the gain depends on RF and R1 values. Gain depends on RF and R1 values, right? So similarly, if VA equal to 0, so the configuration is, the circuit becomes a inverting amplifier. If VA equals 0, sorry, the circuit becomes a non-inverting amplifier. So this we can write here V1 equal to, so what is V1? So V1 equal to R3 by R2 plus R3 into RB. Okay. So here V1 equal to R3 by, so using voltage divider rule, this we can write R3 by R2 plus R3 into VB. Okay. So that is the voltage at V1 node. So V1 equal to R3 by R2 plus R3 into VB. So the output due to VB, see here the output due to VB. So this we can write, so 1 plus RF by R1 into 1 plus RF by R1 into this V1. Okay, the output due to VB. Okay, when VA equal to 0, it becomes a non-inverting amplifier. So for the non-inverting amplifier, the gain is 1 plus RF by R1. 1 plus RF by R1. So the output voltage, so we can write 1 plus RF by R1 into V1. Here the input is V1, right? So the output due to VB equal to 1 plus RF by R1 into R3 by R2 plus R3 into VB, right? So here if R1 equal to R2 and RF equal to R3, then we can write V0 due to VB equal to RF by R1 into VB. Okay. So that is output due to VB. Here the output due to VA is this one, minus RF by R1 into VA. Okay. So these are the two outputs in this differential amplifier. So add these two outputs. So then the total output voltage V0 is equal to, so V0 of A plus V0 of B. So this we can write RF by R1 into minus VA plus VB. Okay. So that is the total output voltage for the differential amplifier. So differential amplifier consists of both inverting amplifier and non-inverting amplifier, right? So the gain, see here, so the gain due to Inverting amplifier is, so the gain of the inverting amplifier is minus RF by R1, and the gain of the non-inverting amplifier is 1 plus RF by R1. Okay, and find out the output voltage V0 of A and V0 of B, and add these two outputs, V0 equal to V0 of A plus V0 B, then you will get V0 equal to final output voltage RF by R1 into minus VA plus VB. Okay. Next we will see the DC characteristics. DC characteristics of op-amp. So we have different characteristics. Of op-amp. So input bias current, input offset current, input offset voltage, thermal drift, input resistance, output resistance, input capacitance, output capacitance, open loop voltage gain, CMRR, PSRR, output resistance, gain bandwidth product, slew rate, output current. Okay, so these are all the characteristics of op-amp. The characteristics of op-amp are input offset voltage, input offset current, input bias current, input resistance, input capacitance, open loop voltage gain, CMRR, PSRR, output offset voltage, output resistance, gain bandwidth product, slew rate, output current. Okay, so these are the characteristics of op-amp. So in this, the DC characteristics are, DC characteristics are input bias current, input offset current, input offset voltage, and thermal drift. Okay, the DC characteristics are input bias current, input offset current, input offset voltage, and thermal drift. So we'll see what is input bias current. Input bias current. Okay, input bias current. Here the two currents are flowing through the op-amp, IB1 and IB2. Right? The two currents are flowing through the op-amp, IB1 and IB2. So input bias current is, it is the average of two input currents flowing into op-amp. It is the average of two input currents flowing into op-amp. That is the input bias current. So we can write IB equal to IB1 plus IB2 by 2. IB equal to IB1 plus IB2 by 2. So it is the average of two input bias currents, flowing into op-amp. Okay. So IB equal to IB1 plus IB2 by 2. So that is the input bias current. See here. So current. So here IB plus and IB minus. So IB plus flowing through the compensating resistor. So it is a compensating resistor. So it is IB plus is flowing through the compensating resistor or COMP or compensating. So then if you apply KVL, so we get V0 equal to V2 minus V1. V0 equal to V2 minus V1. So by selecting proper value of compensating resistor, V2 can be cancelled with V1 and the V0 equal to 0, right? So this you can write V1 equal to, so that is V1 by R compensating. So the purpose of compensating resistor is to minimize the offset values. Using the compensating resistor. Okay. So here I1 equal to V1 by R1. You can write I1 equal to V1 by R1 and I2 equal to V2 by RF. So this voltage is V2 and this voltage is V1. So we can write I1 equal to V1 by R1 and I2 equal to V2 by RF. Okay. So from this equation 3 we can write V2 equal to V1. We can write V2 equal to V1. So that ID equal to V1 by R1, V1 by RF, V1 by RF. So here I1 equal to V1 by R1 and I2 equal to V1 by RF. Here V2 equal to V1. So I2 equal to V1 by R1. So next, input offset current. Input offset current. IIOS. IIOS. Offset current. Input offset current. So we can write IIOS. So input offset current is the difference of two input currents flowing into op amp. It is the difference of two input currents flowing into op amp. Okay. So the two input currents are IB1 and IB2. So we can write IIOS equal to IB1 minus IB2. IB1 minus IB2. So it is the input offset current. It is the difference of two input currents flowing into op amp. Okay. So offset current IIOS for BJT op amp is 200 nanoamperes and FET op amp is 10 picoamperes. Okay. So IIOS for BJT op amp is 200 nanoamperes and FET op amp is 10 picoamperes. So that is the input offset current. So next we will see input offset voltage. So what is the input offset voltage? Input offset voltage. So whenever both input terminals of the op amp are grounded, so ideally the output voltage should be 0. Clear? So if the input terminals of op amp are grounded, if the input terminals of op amp are grounded, so ideally the output voltage should be 0. See here, so the two input terminals of op amp are grounded. Ideally now the output voltage should be 0, but in practice op amp shows a small non-zero output voltage. But in practice op amp shows a small non-zero output voltage. So this is due to the mismatching of the internal circuit. So when the two inputs are grounded, the op amp, in the ideal case, the op amp output must be 0. Okay. But in practice it shows some value. So it is due to the mismatching of the internal circuit. So due to the mismatching of the internal circuit, when the two inputs are grounded, the op amp output shows some value. Okay. To make such a voltage 0, apply a small DC voltage between two input terminals. Apply a small DC voltage between two input terminals. This DC voltage is called input offset voltage. That DC voltage is called input offset voltage. Clear? See here. In the ideal case, if the two inputs are grounded, the op amp output voltage must be 0. But in practice, when the two inputs are grounded, the op amp output voltage shows some value. So to bring that voltage to 0 level, we are applying the DC voltage between the two input terminals. That voltage is called as input offset voltage. So that is called input offset voltage. Okay. So DC characteristics are input offset voltage, input bias current, input offset current. So input offset current is the difference of two input currents flowing into op amp, that is IB1 minus IB2. Input bias current is the average of two input currents flowing into op amp, that is IB1 plus IB2 by 2. And the input offset voltage whenever both input terminals of op amp are grounded, so ideally the output voltage should be 0, but in practice op amp shows a small non-zero output voltage, so it is due to the mismatching of the internal circuit. So to make such a voltage to 0 level, apply a small DC voltage between two input terminals. This DC voltage is called input offset voltage. Okay. Next is output offset voltage. So it is the DC voltage presented at the output terminal when the two inputs are grounded. Output offset voltage. So output offset voltage means, in the practical case, if the two inputs are grounded, the output shows some value, so that voltage is called as output offset voltage. Okay. So next, what is thermal drift? Thermal drift. So it is the average rate of change of input offset voltage per unit change in temperature is called thermal voltage drift. So that is delta VIO by delta T. Delta VIO by delta T. Okay. Thermal drift is the average rate of change of input offset voltage per unit change in temperature is called thermal drift, thermal voltage drift. So this can be written like delta VIO by delta T. Delta VIO by delta T, that is the thermal drift. Okay. Next, see the AC characteristics. AC characteristics. The AC characteristics are frequency response and slew rate. Frequency response and slew rate. So we will see what is frequency response and what is slew rate. Okay. So the variation in operating frequency will cause variations in gain magnitude and its phase angle. So the variation in operating frequency will cause variations in gain magnitude and its phase angle. So the equivalent circuit of op amp. So Vd is the difference voltage, is the input resistance. So it is AOL V2 or Vd. So voltage generator. R0 is the output resistance. Okay. So from this circuit we can write V0 equal to minus JXC by, so from this circuit we can write V0 equal to minus JXC by R0 minus JXC into AOL Vd. So V0 means, so how to get V0? That is the voltage across capacitor. It is the voltage across the capacitor. So this impedance, it is minus JXC by R0 minus JXC into AOL Vd. Okay, so that is V0, minus JXC by R0 minus JXC into AOL Vd. So open loop voltage gain, where AOL is the open loop voltage gain, Vd is the difference voltage. So this we can write A equal to V0 by Vd. Okay, so from this equation V0 by Vd is AOL by, so this we can write 1 plus J 2 pi f R0 into C, and A equal to AOL by 1 plus J f by f1. One second. Okay. So AOL by 1 plus J f by f1, where f1 is 1 by 2 pi R0 into C. Here where f1 is 1 by 2 pi R0 into C. The magnitude of A equal to AOL by square root of 1 plus f by f1 whole square. So mod A equal to AOL by square root of 1 plus F by F1 whole square. Okay. So for frequency F is less than F1, the magnitude of the gain is 20 log AOL in decibels. For frequency F is less than F1, see here the frequency F is less than F1. So for example, if it is F1, this range is the frequency at which F is less than F1. Here the magnitude of the gain is 20 log AOL. So the magnitude of the gain is 20 log AOL. Okay. So at frequency F equal to F1, the gain in 3 dB down from the DC value AOL in dB. So this frequency F1 is called corner frequency. So at the frequency F1, so that means at F equal to F1, the gain decreases by, here the gain decreases by minus 20 decibels. The gain decreases by minus 20 decibels. For F is greater than F1, the gain decreases at the rate of minus 20 decibels per decade. Okay. So for the frequency F is less than F1, so in this frequency range, for the frequency F is less than F1, the magnitude of the gain is 20 log, see here. So in this range, the magnitude of the gain is 20 log AOL, that is in decibels, 20 log AOL. So at F equal to F1, it decreases by minus 20 decibels per decade, right? If the op amp operates with more than one corner frequency, here this frequency is called as corner frequency or cutoff frequency. Corner frequency means at this frequency the gain decreases by minus 20 decibels per decade. This frequency is called as corner frequency or cutoff frequency. Okay. If the corner frequency is 1, if it has one corner frequency, so it is, the gain is AOL by this one 1 plus JF by F1. Okay. Then the magnitude of gain is mod A equal to AOL by square root of 1 plus F by F1 whole square. If the corner frequency, it has a single corner frequency. If the op amp operates with more than one corner frequencies, then the gain becomes, so AOL by 1 plus JF by F1, 1 plus JF by F2, 1 plus JF by F3. Okay. So the gain with 3 corner frequencies. The transfer function is the gain with 3 corner frequencies. If it is one corner frequency, then we can write A equal to AOL by 1 plus JF by F1. But if the op amp operates with more than one corner frequency, so here you have 3 corner frequencies. So the gain becomes A equal to AOL by 1 plus JF by F1, 1 plus JF by F2 into 1 plus JF by F3. See here. So at F equal to, so at F, when F is less than F1, the gain is minus 20 decibels per decade. Here after F1 it decreases by minus 20 decibels per decade. Again after F2 it decreases by again minus 20. So here we get minus 40. After F3 it becomes minus 60 decibels per decade. It contains 3 corner frequencies, right? So next characteristic is slew rate. Slew rate. What is slew rate? So another important frequency related parameter of an op amp is the slew rate. So slew rate is the maximum rate of change of output voltage with respect to time. Slew rate is the maximum maximum rate of change of output voltage with respect to time. It is specified in volts per microseconds. So S equal to maximum rate of change of output voltage, so delta V naught with respect to time. So S equal to delta V naught by delta T. S equal to delta V naught by delta T. Okay. So slew rate is the change in output voltage with respect to change in time. Slew rate is the change in output voltage with respect to the change in time. So S equal to delta V naught by delta T. This is specified in volts per microseconds. Volts per microseconds. So what is the reason for slew rate? Why the output changes with respect to time? Here the output changes with respect to time, right? So delta V naught by delta T. The output changes with respect to time. So what is the reason? Why the output changes with respect to time? Here, so there is usually a capacitor within or outside an op-amp oscillation. So this capacitor prevents the output voltage from fast changing input. So this we can write dV by dt equal to I by C. So slew rate equal to dV naught by dt. So for a sine wave, so if Vs equal to Vm sin omega t, if Vs equal to Vm sin omega t and output equal to Vm sin omega t. So it is a voltage follower circuit, right? So in the voltage follower circuit, V naught equal to Vin. If Vin or Vs equal to Vm sin omega t, then the output is also same, V naught equal to Vm sin omega t. Here the rate of change of output is given by dV naught by dt equal to Vm omega cos omega t. dV naught by dt equal to Vm omega cos omega t. So the maximum rate of change of output across when cos omega t equal to 1, right? So this we can write SR slew rate equal to 2 pi f Vm, 2 pi f Vm. Okay, it's the maximum frequency. So F max is the maximum frequency. Okay, so slew rate S equal to 2 pi f Vm. So that is the slew rate. So slew rate is the change in output voltage with respect to change in time. So S equal to delta V naught by delta T. Okay, with this I am going to stop the presentation. In the next session, so we will discuss about frequency compensation techniques. Okay, so if you have any doubts, you can ask me.